So going back to the infrastructure system problem and the pavement management problem. So now this allows us, if you were to have a web-based interactive decision support system, well, what are the different components? Well, going back to the explanation level, the domain-specific models, you have, again, within that, we have to look at it at different scales. We have the activity scales, where we're looking at activity-specific emission cost, emission cost and usage data. So for a particular earthwork operation, what kind of equipments are we using? How much fuel are we using on these equipments? How long is our schedule? Okay, that goes on to a project level. At the project level, if you were to choose a particular design, then over the life cycle, what are the impacts of that particular design? And going all the way up to system level, where we're looking at operational environmental metrics, where you say, well, do we really need more highway capacity in a particular region? And if we need more highway capacity, who are the people who are being affected? What kind of value are we delivering? And that is where, of course, if we realize that as we go further up the scale from the micro to the macro across those different levels, our complexity increases. So while you're at the activity level, it's far more easy to actually put it down to numbers and calculate and measure. But as you go further up, you realize that you have to start working with social scientists and start talking about what are all the broader impacts. And then you take that, and once we have that understanding, that can go into the integrative models. Right now, in terms of where we are with our research, we have a lot of the stuff that we've completed a lot of the stuff in that box. We have an idea on how to do explanatory models, but we're at the process of creating more integrative models that can. Interestingly, we have the explanatory models. We also have the technology to do the predictive and exploratory stuff. And what we're really filling in is the spot in the middle where we're trying to come up with our and twiddle with our representational mechanisms. So this is we just visited that network, and what we have here is an example of a situational simulation for an infrastructure system, or where you have one or more codependent infrastructure systems. And this I spoke about querying future spaces, and what you see up there is a little impact probability curve. And this is not very clear. It's more of an idea that I'm presenting to you. But if you're interested, this is something we could sit down together and give you a demonstration and run of. And then as you're doing this, what it is doing, interactively giving you information, feeding you back information in terms of what are your edge capacities like, what is the capacity within your network at that point. If there were external events, catastrophic events, how does that impact your network? And as we go through it, I have very simple metrics that we are measuring out here, which is edge weights. So if there is something that's going wrong, you start seeing your edge weight fluctuating over time. And also what your impacts are, and we're early in the simulation, you can see your impacts. A little blip down there. So, in summary, I do want to keep some time for a conversation. In summary, what I've presented out here is sustainability is an integrative method to defining and addressing problems. And no, it's not just about the environment, because if you're making sustainability just about the environment, we're making the same mistakes that has led us to the mess we're in today. So it has to be about everything, and it's easier said than done. But we really need to come to a point where we start addressing a methodology that is inclusive at a methodological level, and also inclusive at a human level, because ultimately there is a very strong component. There's a very strong human and methodological component to sustainability. So fundamentally, it's going back to that perspective where we can take best advantage of our reductionist approaches while being able to put it all in within the broader systems picture. Acknowledgement, primarily there's a lot of faculty I work with and I enjoy working with. Get a lot of very significant feedback from Dr. Onder. Jim's not here anymore, but Jim was and continues to be a great support. Of course, Bill and Chris, I get the maximum, managed to harass them enough. And of course, John and Dana and Roger too. So, I'll leave it at that. Sure. Yeah.
Did you have to deal with changes in network topology when you integrated networks? I was curious.
Right. So.
Imagining is you have point A, point B, and M is a road.
Right.
But if a water leak affects a road, then the population
is gone. Right. Right. Absolutely. So what if you go back to that network diagram out there? That's actually a great question because where was I? There. So, for example, when we have a failure in a node, in an edge, do we change the network topology? And the answer is no, you don't, because you maintain because we don't want to get into the related complexities. But we want to keep the network topology as is. But what we can do is we can change the edge properties. And so we right now what we're doing is giving fairly the data structures are fairly heavy on the edges on the nodes. And again, this is an operational thing that which with time can change. So for example, if there is a failure, what you would have is the capacity would go to 0. So your edge still remains, but the capacity has gone to 0. Now once the capacity has gone to 0, you can see the impacts of that 0 capacity on neighboring edges and neighboring nodes. And that's also, it also provides you a way of looking at impact of micro events on macro behavior within the network. Does that answer your question? Roughly. Sure. Go.
So in any of the systems analyses that you've done, have you seen anything that you would call emergent that's surprising?
So,
however you want to define surprising.
Well, I think some of the patterns that we're finding with the sewer network, as well as the water network failure data, I think is interesting. But it's not emergent. It's very interesting. That's one of our interesting finds, so to say. Among other interesting behaviors that we're looking at is, so for example, the Braze paradox, where you have, so giving you an example, is that where sometimes adding, not sometimes, typically you find that adding more highway capacity actually increases congestion, does not reduce congestion. This is a well-established result. So we are finding similar behaviors, but no, we haven't gotten to a point within infrastructure networks where we're finding some direct patterns like that. But we did a study with construction congestion, and we used an agent-based model for construction congestion. Again, it's a systems method applied to a very, very small, very reduced problem. And what we found out there was within our little toy simulation, we could actually replicate all the most of the very critical rules that people follow when they're looking at labor on construction, when to hire and fire labor, or what to expect in terms of productivity and space distributions. So some of that stuff. This is still early, so. I guess I kept my promise on time. Well, no more questions?
Waiting for a question?
Yeah. Well, I think we're done. I know. Thank you.